who are new, we at CoffeeShop Astrophysics are a group of grad students and postdoctoral researchers that work in the Center for Gravitation, Cosmology, and Astrophysics at the University of Wisconsin, Milwaukee. We like giving these talks, so we like talking about science, and luckily we have an audience that comes regularly. So today, your two speakers will be my friend Ali Spaulding, who is over there, and myself, Alex McEwen. And we're going to be talking about the scientific method. But before we get into that, if any of you have any ideas for scientific talks that you'd like to hear or are interested in learning more about, please send those to us. We'd be happy to work them into our schedule. So you can either send an email to coffeeshopastrophysics@gmail.com, or there's actually a sheet down next to the door where you can write down topics that you're interested in. Hey, Sarah, can you turn it up a little bit? Yes, so today's presentation, like I said, is about the modern scientific method as we use it as astronomers. So, you've all probably heard of the scientific method, and you've likely maybe even used the scientific method explicitly in a science fair experiment, or for yourself, or maybe your kids. You're probably familiar with the steps, but I'll go through them anyway. The first step is to state some problem or question that you have about the world, or the universe, or maybe the weather. Next, you can formulate a hypothesis using your previous knowledge about whatever it is you're interested in. Once you have a question and a hypothesis, you can design an experiment which will help you learn about that hypothesis and test it. Take data from your experiment, analyze those data, and ultimately draw some conclusions about how the world works. Now, I'll admit, when I was choosing pictures for this slide, this wasn't necessarily my favorite picture for the scientific method, but it had one thing that I liked a lot, which is that it ends somewhere different from where it starts. So that's the whole driver behind using the scientific method and doing science, is to learn new things about the universe. So before we get into the astronomy stuff, which I promise we will get into, I just wanted to go through a quick non-astronomy example of the scientific method so that we can all get on the same page here. So one question that I have has to do with the fact that every year I try and plant vegetables, and every year they die, and I don't get any vegetables from them. So in order to figure out a way forward with this, I might ask the question, what fertilizer can I use that will make me get the most vegetables from my plants? So, naively, I might think cost must scale with effectiveness for fertilizer. That is, the most effective fertilizer would be the most expensive. So I'll make my hypothesis that the most expensive fertilizer will do the best, and as I go down in price, I will produce fewer and fewer vegetables. And at the very least, having no fertilizer should do the worst. So some sort of fertilization should help with growth of my plants. So now I have a hypothesis, I have a question, come up with an experiment. My experiment will be to plant 4 identical tomato plants using either the most expensive, second most expensive, or the cheapest fertilizer, and compare that to one where I did not use a fertilizer. And at the end of the season, after I've grown my plants, I'll count all the tomatoes I get from them, and I can see whether or not my hypothesis is supported by my data. So I plant my plants, let them do their cool thing that they do, turn into tomatoes, and at the end of the season, in August, so it's not freezing cold anymore, it's now hot, I count all my tomatoes, and I see that the unfertilized plant only produced 1 tomato, the cheapest produced 2, the second cheapest produced 5 small tomatoes, and the most expensive produced 2 large tomatoes. So I can see, at least from this, fertilizer seems to have some effect. So that's one part of my hypothesis that has support. But other than that, it seems as though the relationship between the price of the fertilizer and the amount of tomatoes I get is not so straightforward, right? So there's some other things, there's other variables to consider here. So maybe I haven't directly answered the best way to get tomatoes from my crops, but at the very least, I have new information, I can design new experiments, and I can go forward next year trying out different things to continue to optimize my plant growth. So that's our non-astro example. Unfortunately, there's one large complication for astronomy, which is namely that we can't interact with our test subjects in any way other than looking at them, right? We can't touch them, we can't taste the tomatoes at the end of the season. So you can imagine trying to do that same experiment, trying to figure out how to best grow tomatoes, but you're only looking at tomatoes that are a billion, jillion miles away. You can't tell what's in the soil, you can't even tell how big the plants are. It's a lot more difficult. Fortunately, we have millennia of people thinking about astronomy and looking at the stars and learning information little bit by little bit, following the scientific method. And so now we have tons of information and tons of ideas and theories about how the universe works. So I'm going to talk a little bit about what that means for us, though I'll say the stating a problem and a hypothesis follows pretty similarly to the plant question, really. You know, we have things we can see, we can come up with questions, we can come up with hypotheses to answer those questions. But really where it starts to diverge is in the experimental design. So I split this up into observational and theoretical experimentation. But really, you know, these things go hand in hand. They're very synergistic. They both help each other. And we all really use both types of experiments. But it's a little bit easier to think about them in these split up like this. So on the observational side, which is more the kinds of research that I do personally, this is where we're actually using telescopes like the Green Bank telescope down here. That's the one I use the most. We use them to actually look at these stars and take data. And when we're planning to do that, we need to figure out what kinds of measurements we can make that will forward our knowledge as much as possible. That's what we want, is to gain as much information about the world as we can from as little data as possible. So once we have an idea of what we might want to measure, we need to consider what we're looking at and try and predict how it will act when we take our data, when we actually do these observations. If we can predict the way that it works, then we can at least hopefully guarantee that our test will go the way we want it to and we'll learn something at the end. Once we have that, we can try and optimize that experiment to really get the most information out of it, and then we can actually propose for and conduct these experiments, so take data with a telescope. On the theoretical side, it's a little bit different. So usually the main driver for theoretical experiments is about discerning which theories do the best job of explaining the universe, and also how we can actually test the validity of those different theories. So once you have multiple theories to describe how some sort of star works, or galaxies, or whatever, you can create simulations of different galaxies that evolve following different rules of science, different mathematical theories. And we can see how those different galaxies we've simulated differ from one another. So what things should we expect to see in a galaxy that forms according to theory A compared to theory B? If we can isolate those things that are different, we can come up with experiments that will target those differences and nail down which theories actually represent what is happening in the physical world. So this little GIF down here is actually from a video game called Universe Sandbox, which I highly recommend if you've never heard of it before. But you can create little simulations of stars and galaxies and crash them into each other, right? Because that's the most powerful tool in the simulation world, is once if we have a model that accurately describes how something works in the physical world, then we can change the fertilizer in our plants. We can test whatever we want and throw other stars at it. We can, look at whatever things we're interested in looking at because we are in control of that experiment. So all these things play together to help us forward and learn new things about the universe. So one sort of digression is when you're designing these experiments, you really have to choose the proper instruments to use depending on the experiment you want to do. So we have 4 different telescopes here. The one in the upper left is the one I've talked about before. That's the Green Bank telescope. And it takes data in radio light. So just like in your car stereo, it's listening to radio light from outside of Earth. On the upper right, we have the Spitzer telescope. So this is in space and observes light in the infrared. So infrared gives us information about temperature of objects. So we can look with Spitzer if we're interested in seeing how temperature might change in different places of the universe. Bottom left, anybody know what this one is? Yeah, that's the Hubble. Yeah, so pretty well-known one. This is another space telescope that observes invisible light. So Hubble takes pictures that are similar to what we could see if we could, look millions of years into the past and far away from Earth. And then finally, in the bottom right here, we have the Chandra X-ray telescope. So this telescope sees light in X-rays. Now, as you can imagine, these give us very different pictures of the universe. And as an example, I have 4 images of Jupiter taken with these different wavelengths. So you're probably most familiar with this representation of Jupiter, which is what you see most of the time. But you can see there's lots of other information that we can get just from looking at it at different frequencies. So when we're trying to design an experiment to learn something about the way the world works, we need to choose our telescopes to fit those experiments. And I mean, this goes down not only to the light, but also the way that the light reaches us, right? So people often wonder if me, as a radio astronomer, if I use telescopes that are orbiting Earth, and I don't. The reason why is that radio light passes right through our atmosphere without any problem. So we can take observations during the day, anytime we want, and the atmosphere doesn't cause problems. But if we put Hubble on Earth and tried to observe space, during the day it would see a nice bright blue sky, but it wouldn't necessarily see the stars behind it like we can. So that's another important factor when coming up with these experiments. So now we've established what our experiment is going to be. We figured out what we want to observe, how we want to observe it. Now we beg our astronomy or our observatories or supercomputers to do our experiment, please. So we have to write proposals where we tell them what it is we want to observe, how we want to observe it, and most importantly, why we want to observe it. So what is the information that we're going to take away from this experiment? Now, I say observatories, but in the case of Allie, this is more on the simulation side, so this is requesting time on big, beefy computers that can do lots and lots of simulations that are too taxing for our laptops. So we submit our proposals, we get our data, and now we have to analyze that data. So these are a whole bunch of examples of different things that we see in our data that are, that we have to mitigate in some way. So in the upper left panel here, this is a representation of a pretty common technique in astronomy called noise subtraction, where we say we have some, in this case, a nebula that we're interested in looking at. So we take an observation and we have that nebula, but we also have a bunch of other stuff in this image that we're not as interested in. And that other stuff will contaminate our measurement of that nebula that we are trying to look at. So we use what we know about the different sources of noise. Sources of noise include space dust and background stars and telescope stuff. And we try and remove those artifacts from our data. In the upper right here, we have 2 images of the same galaxy taken by Hubble before and after it had a lens problem corrected after it first went into space. So you might see that this left picture is much fuzzier than the one on the right. So you can see these are the sorts of effects we have to analyze in our data. Down here we have basically this is actually not from a telescope, but it's from a receiver that works in a similar way that a telescope does. And it's basically just measuring how bright light is on this receiver as a function of the color of that light. And what's happening as it switches, as it flips back and forth here, is that there's a tiny LED that's being turned on and off next to the receiver. So you can see that when that light is on, we suddenly totally lose all these interesting features in our data, because that little source of light is bright enough to just blow it out of the water. You can imagine like looking at a candle that's in front of a spotlight, right? It's just totally blown away. And this last image is a simulated image of Starlink trails in astro data. So I don't know if you're familiar with Starlink. It's the Elon Musk's solution for internet for everyone. Yeah, and you can see it causes some difficulties for astronomy. So these are the sort of things we have to work out. We have to remove these from our data to make sure we get the information that we want from it. On the side of simulations, where we're not actually looking at data that's taken from a telescope, that is, we need to make sure that these models that we're using do the best job to simulate what it is that exists in the natural world. This first picture is a couple of frames from a simulation where two stars are orbiting each other really tightly, and one of the stars is big and puffy and gets shredded apart by their movement. So as time goes on, after 240 days, you have this big, puffy cloud of dust that's left over from these stars ripping each other apart. In the top right, we have 3 panes of simulated galaxy as it evolves over many billions of years. And it's a little dark, but there's an image of an actual galaxy that looks as though it represents, this simulation data represents that galaxy pretty well. So that means that our model does a pretty good job of ending up where nature has ended up over the course of time. Finally, this last simulation is even larger scale. This is on the universe-size cube, basically, where over the entire lifetime of the universe, gas and dust and stuff slowly collapses down into this sort of structure that we actually see in our universe now. So the only way that we can get to those endpoints that match reality is if we have a good model to describe the way that they evolve over this time period. Finally, the last thing that we do after we've done our experiment and got our data is we share that information with other people in the community. And this is through talks like this. It's also talks with different scientists. We write papers, publish papers, and share them on this Astrophysics data system where you can look up any paper that's been written and submitted in astronomy for the last 150 years or something like that. And I was too embarrassed to share a picture of a paper that I've worked on, so instead I'm just embarrassing Allie by showing one of her papers. But yeah, so this is the main way. We discuss these results, we share them with the scientific community, and we encourage that people try and reproduce them. Because if we can have multiple tests, multiple people coming up with their own ways to test the same things, if we all end at the same place, then that's much more evidence that we're following the right train of thought, basically. So, with that, I'll hand it over to Allie.
Can I have the clicker? The clicker. Okay. Thanks for the shout out. So Alex talked a lot about the specific steps of the scientific method and how we use our techniques in the research we do today. And now I'm going to go through more of the evolution of the scientific method and specific examples of experiments and how we've conducted each step. So to start, pre-Renaissance time, before the 13th century, experiments were more based on philosophy, logic, and truths. So it was more about a thought experiment, and if you could talk it out and convince yourself, then you're probably right. Good thing we evolved from there. So starting in the Renaissance times, we started to collect data. It became more important. The microscope was invented and the telescope was invented. So the movement towards getting actual data started becoming bigger. And then where we're at today is our technology is more advanced. So the method, is the same steps, but now with advanced technology, we can get more data, and we're better at confirming or denying the theoretical theories and matching them with actual observational data. So we're more on the step of advanced techniques and technology. Okay, so just going through some examples of experiments that have used this method. If we go back to one of the earliest experiments of astronomy, ancient Greek philosophers had the question of, is everything revolving around the Earth, or is everything revolving around the sun, or just more generally, how are the planets orbiting in the universe. So there were two camps of thought. One group thought that we were the center of the solar system, of course, and then another group thought that maybe the sun is the center of our solar system. Aristotle strongly believed that we were the center of our solar system, and his thoughts prevailed for a very long time. And then an astronomer came up with the question of, are we really the center of our solar system, or is there more than just us? So a Polish priest, Nicholas Copernicus, who you've probably heard of, proposed the hypothesis that maybe the sun is at the center of our solar system in 1515. He didn't publish his theory until 1543, shortly before his death, probably because this theory went strictly against the teachings of the church, which was not something you did in that time unless you wanted to be excommunicated. So, to design this experiment, there's not much you can do in the 16th, 17th century, except for looking up in the sky and maybe writing down your observations, but nothing too fancy. Okay, so then we have another astronomer who you've probably heard of, Galileo, who believed this Copernicus idea that the sun was actually at the center of our solar system. So in 1610, he used a fancy telescope that probably looks something like that, and he, for the first time, observed 4 moons orbiting Jupiter. And when he gathered his data, it was probably something as simple as just drawing exactly what he saw in the sky. So these moons are now called the Galilean moons, since he was the first one to observe them around Jupiter. So his conclusion when he analyzed this data was that if all things orbited the Earth, these moons could not exist because they are not orbiting the Earth. Therefore, the geocentric view of the Earth being at the center cannot be correct. So around the same time, a German mathematician, Johannes Kepler, used this same idea that the sun was at the center and came up with 3 mathematical laws to describe the orbits of the planets with the sun at the center. These are still laws that we use in physics today. So the first is that planets move in elliptical orbits around the sun. So before this, planets were assumed to move in circular orbits, but he actually found that they're more elliptical. The second is that a line segment joining the planet and the sun sweeps out the same amount of area in equal time intervals. And then the third is this relationship between P, which stands for the period of a planet, so how long it takes to orbit the sun, and A, which is the distance between the planet and the sun. So this relationship says that those two are proportional to each other, just meaning that the closer a planet is, the shorter it takes to orbit the sun. Eventually, Isaac Newton came around and gave the force that governs these laws a name that you've probably heard of, which is gravity. Okay, so in conclusion, for this experiment, they found that heliocentrism is the correct model. The solar system does not revolve around us. Another conclusion that they used a lot in this time was Occam's razor, which basically just says that the simplest explanation is usually the best. So when 2 theories were competing against each other, a lot of times they just said the fewer assumptions, the better. And this view of heliocentrism used the least amount of assumptions. All right, so that's probably the earliest example of the scientific method in astronomy, or one of them. Now I'm going to go a little bit more current. So Alex talked about how a lot of times in astrophysics research and astronomy research, we start with a mathematical theory that we believe models the universe, and we run tests to see how complete or correct this theory actually is. So one of those is the theory of general relativity. So first I'll explain what this theory says. So it is also known as Einstein's theory of gravity, and it is the geometric theory of gravity. So before Einstein came up with this theory, we had Newton using his law of gravity describing the universe. And he defined gravity as the force of attraction that 2 objects exert on each other. So gravity depends on the mass of 2 objects and then the distance between them. The more massive object will feel the greater pull. For example, the Earth is pulling on us. Thank goodness, that's why we stay on the Earth. But we are also pulling back on the Earth. Since we're so much less massive, the Earth doesn't care, doesn't feel us at all. And that's what Newton was saying. But then Einstein came around and said that space and time are actually interwoven into a single continuum known as space-time. So Newton described gravity as an innate force, but Einstein said actually space and time are interwoven. So that's a little confusing. What he's saying is if you think of putting an object on a trampoline, if you put a large object on a trampoline, and let's say you throw a marble around it, the marble will orbit it, and then it'll be tugged into the larger object. And that's exactly what's happening with planets and large objects in space when things are orbiting around it. And then the best simple explanation that I like for general relativity is that space-time tells matter how to move, and matter tells space-time how to curve. Okay, so this is the theory that Einstein came up with, and there are a couple tests that we can run to see how complete this is. If we start with our question, we can ask, is Newton's universal law of gravitation correct and complete? Well, Einstein hypothesized that the curvature of space-time is directly related to the energy and momentum of whatever matter and radiation are present. So like I said, that matter tells the space-time exactly how to curve. Or in math language, something like that. Okay, so before Einstein's time, actually, astronomers noticed that Mercury's orbit was slightly changing over time. And so they designed this experiment by taking observations of Mercury's orbit over time, and they used math to turn this into what's called an angle of precession, which is basically just a rate of exactly how it's changing over time. This is a pretty good experiment because Mercury has a short period, since it's so close to the sun, of only 88 days, and we can view it every 3 to 4 months from Earth. And the goal is to compare this observed precession rate with the theoretical answer given first by Newton's law of gravity and then by Einstein's theory of gravity, or general relativity, and then comparing which mathematical theory gives us the same as that observed rate. All right. So like I said, this actually started before Einstein even had his theory of general relativity. In 1859, Urbain Jean-Joseph Leverrier used 14 observations of Mercury's transit time taken around the 18th century. He worked at the Paris Observatory, so he probably just had simple instruments like this. On the right is a reflecting telescope, so it uses mirrors, and then the left is a refracting telescope, so it uses lenses to focus the image. And when they gathered the data, they found that Mercury was observed to precess at 565 arcseconds per century. So arcseconds is a unit that we use for angles in astronomy and astrophysics. Because the angles we're looking at are so small, if we use degrees, we would have to have a lot of decimal places to see differences. So we use this unit of arcseconds. And today they've done this experiment or observed Mercury a lot, and it's actually closer to 574 arcseconds per century. So we have our gathered data, and then when they analyzed it, so before Einstein was around, they just used Newton's law of gravity, and what you can do to calculate it is compute the gravitational force from every planet on Mercury, and that will give you your precession rate. So they did that using Newton's laws and only found a rate of 531 arcseconds, which was a good amount off from what they actually observed. So for a while they were just like, this is weird. There must be a missing mass somewhere that we didn't account for. So either their calculations weren't correct or their theory wasn't correct. So then Einstein came along and introduced general relativity. And once you do the whole math for that, you get an added shift of 43 arcseconds. Put those together, maybe, and you get your observed rate that matches exactly to 574. So this is one of the first experiments that gave us more evidence that general relativity is the more complete theory for gravity so far. Okay, a more modern current experiment for general relativity. If you've come to our talks before, I'm sure you've heard of gravitational waves. So, same problem. We always need more tests to compare and confirm these theories to make sure that they correctly explain our physical universe. So in 1916, Einstein hypothesized that massive accelerating objects, such as neutron stars or black holes that are orbiting each other, would disrupt space-time in such a way that actual waves of space-time would propagate in all directions away from the source. So he predicted these in 1916. And then in the 1980s, scientists at Caltech decided to design an experiment to observationally test for these gravitational waves and see if we could detect them on Earth. Okay, so to do this, they used what's called an interferometer. The long name is Laser Interferometer Gravitational Wave Observatory, or LIGO. There's a huge group of LIGO people at UWM. I'm not one of them. So if you have questions, ask them. But it's a huge collaboration today, which is really cool. So when they started the experiment, they used an interferometer. On the left, I have a basic picture of it. It's used in a bunch of experiments, the general setup. And what happens is a laser comes into what's called a beam splitter, splits the laser, and then bounces back and hits that black detector. And the reason it's called an interferometer is because it measures interference patterns on the detector. So maybe it's a little clearer on the right GIF over there. When the waves slightly shift and come back and go to the detector, they'll create different patterns on that screen. And that tells you that something is shifting and something is changing in the interferometer. So LIGO did this, but on a much, much larger scale. They have observatories with arm lengths of 2.5 miles long. And the reason they're so long is because gravitational waves come in and they'll vibrate those arms ever so slightly, and that causes the arm lengths to change. LIGO is sensitive to a change of 1/10,000th the width of a proton. So like nothing you would feel in your everyday life, a gravitational wave. But the longer the arm length, the more sensitive it is to those slight length changes. So when the arm length changes, that's when the pattern on the detector will change and show you that you observed a gravitational wave. So there's 2 of these observatories in the US. This one's in Hanford, Washington. So this was their experimental setup. In the 1990s, they got those up and running. And then to gather data, they do these runs. They've had 3 so far. The first one was significant because it detected the first ever gravitational wave on September 14th, 2015. And it was of 2 black holes merging together. During the second run on August 17th, 2017, they detected another wave of a neutron star colliding with another neutron star. And this was a super significant signal because it had a lot of electromagnetic counterparts, making it accessible to people in all different types of astrophysics research. And then the third run was divided into 2 sub-runs. And what was significant about that was that they detected a signal of a neutron star colliding with a black hole for the first time. And then there's another run planned for the end of December, so stay tuned for what they detect then. And then I just wanted to show when they detect something, the signal that comes in will look something like that graph up there. And then it has to go into a bunch of analysis techniques to actually get the information that you want out of it. So to analyze the data, Alex touched on this a little bit, but what you can do is compare your actual observed signal to what you would expect to see given the theory that you're trying to test for. So the gray line on this graph is the reconstructed, which just means after it went through all the analysis techniques, took the noise out, that was the actual signal in the detectors. And then there's a slight orange line overlapping, and that's what general relativity would show for a gravitational wave. So this was the first gravitational wave detected, And you can see that it matches the theory perfectly, telling them this is actually a gravitational wave. And Einstein was right again, of course. And gravitational waves are real. So that was really exciting. All right, so what does the future of astrophysics research look like? Today, astronomers can make many predictions on data that hasn't been collected yet. So we use models, simulations, and theory to understand our universe. We think we have a pretty good understanding so far, but gathering real data is extremely hard, like Alex talked about earlier. One exciting advancement in technology is the James Webb Space Telescope, which just launched last December. And it's a versatile instrument that will be used to collect data for many different experiments that are all set up and just waiting for that data, basically. So Alex touched on the Hubble Space Telescope a little bit. What's exciting about the James Webb Telescope is it's an infrared space telescope. So it will see light in the IR wavelength band. It's sensitive to longer wavelengths. The Hubble saw information in the visible light spectrum and a bit of the UV. So basically this instrument is a big advancement just because it gives us more research or more information that we can use for research because it can see in longer wavelengths. So there are 4 themes of the James Webb and goals. The first is to study the end of the dark ages, meaning the first light and reionization of our universe. They want to study the assembly of galaxies, the birth of stars and protoplanetary systems, and then planetary systems and origins of life. So it's really focused on studying the history of the universe and how things become what they are. So I just wanted to pick one of these goals and give you an example, because this talk is on the scientific method, about how somebody could use the scientific method to accomplish one of these goals. So an example of an experiment is if we look at the goal of studying the assembly of galaxies, one open question is in astronomy is what gives galaxies their shapes that we see today. So on the upper right, I have a picture of very distant, so very young galaxies that look a lot clumpier. And then below it is a more current galaxy that we see today, which has that spiral shape that most of you probably associate with galaxies, the same shape as our galaxy today. So a big question is, how did that happen? There's a bunch of hypotheses for this, but one might be that galaxies and stars interact with dark matter, and this gives them their present spiral shapes. So gathering data, that's what the James Webb will be great at. And then once we have that data, we can analyze it by comparing the observed data from the James Webb to different computer simulations that Alex actually showed before of a galaxy evolving with dark matter or a galaxy colliding with other galaxies, and see which one best matches that observational data that we'll get from the James Webb. And conclude whatever we can conclude from there. All right, so that's it for today. Next month, a little less than a month, our topic will be on neutron stars. And we could take any questions now. Thanks.
When does the hypothesis become realized by all of science? Like, is there a level or a certain amount of data that has to be collected?
Yeah, I mean, I would say maybe the question is about significance of the data. So, I can make an observation of something and claim to make a detection, but ultimately I have to show that what I've detected is significant, that it's not just noise, it's not due to some random effect, that I happen to catch in the telescope. And basically that means more observations, more tests to rule out other possibilities. And eventually, you get to a point where you say, the odds of this being not what I say it is are 1 in a billion. So while it's still possible that I'm wrong, the odds are small enough that, then we say, okay, that's likely to be the case. Yeah. Good question. Other questions? Yeah.
Taking the next class,
So computer simulations are great because you can change the parameters easily. So maybe you would start with a computer simulation that has a lot of dark matter and evolve it just a little bit, and then see what the wavelengths in that galaxy are in your simulation, and then compare it to the observed wavelengths that you see in the telescope. Does that make sense?
But you're not detecting wavelengths of dark matter directly.
No. So yeah, you cannot detect dark matter directly. You can only see what's happening around it. Yeah.
One test that has been used for dark matter in galaxies is looking at how quickly material in galaxies is spinning. Basically, like as you go out farther from the center of the galaxy, how fast the stuff is moving. And if we don't have dark matter, basically those should be moving a lot more slowly than what we see them, how we see them to be moving. So what that tells us is there's a whole bunch of stuff in there that we can't detect otherwise that's driving this movement in the galaxies. And because we see that in so many galaxies, it seems pretty ubiquitous. So even though we can't make a direct detection of dark matter, we can see the stuff that it does. We see what effects it has on the other things that we can detect. Yeah.
I have not focused on that at all.
Yeah, I
Yeah.
mean, maybe.
Dark matter is so not well understood right now, so you can probably say that.
Yeah.
Just may go a little beyond the scope of the first talk, but how closely do your astrophysicists talk to nuclear physics?
That's a good question. I mean, I think on some level the line gets a little. Okay, so I should be repeating the questions. The question was, how closely do astrophysicists communicate with nuclear physicists? And I think, on some level, I think the line gets kind of blurred because, when you're talking about stellar, like how stars actually evolve, you're talking about chemical reactions and nuclear reactions inside the star that, take it from a big cloud of gas until eventually it, blows up or does whatever it does. So, we have to have overlap in that sense, right? Because there are people who study those sorts of reactions as much as you can on Earth a lot more closely than astronomers do. So we draw from their results at the very least. Yeah. Hopefully that answers your question. Yes?
In the slide before this, there, it says, the end of the dark ages. I haven't heard that phrase. So, what?
You take this one, Allie.
Something before the Big Bang, right? What is that? Something before.
Yeah, so basically the end of the Dark Ages is just saying, when the universe began. So the goal of James Webb is to look as far back as possible. So, I mean, it's just like a niche-y, like a cute phrase. I don't think it's super specific. The important part is first light and reionization. So more along the lines of the origin of the universe. I don't know. I'm sure that there are projects that are very specifically looking at this, but this is just what's on NASA's website. So.
So reionization, is that referencing when things cooled off enough, when the early universe was a plasma, it was too hot for atoms to form?
Yeah, basically. In the early stages of the universe after Big Bang and things spread out and cooled down, initially when it was really hot, everything was ionized, right? There weren't atoms couldn't hold on to their electrons because photons would just knock them off immediately. As time goes on and the universe cools down, suddenly those atoms can exist, but then eventually stars start forming after a period of time. And those stars start re-emitting new photons from the energy they've created, which then reionizes gas in the interstellar medium. So
is that the 13.8 billion years that we can see back, is that like a veil that we can't see beyond?
It's not exactly. So the cosmic microwave background is from the actual Big Bang, and that's like that's the farthest back that we can see. So we can see evidence of the reionization period in data that looks at stuff that's a little bit closer to us and therefore a little bit more recent in time, but shortly after the Big Bang in cosmological time. I think there was another one. Yeah.
Yeah, can you explain precession again?
At the rate of precession. Yeah, so I think one picture shows it better than others. This one. So, and I probably should have pointed out, in that picture there, that triangle, that's what stands for the angle that the orbit is changing at. So it's slightly, I don't know if you would say moving away from the sun or closer. It depends on where it's at in its orbit. But its orbit is slightly changing. And where that triangle is, that describes how much it's changing by.
Thank you all for coming. We'll see you next time.